Okay, so this next one should go a little faster since we don't actually have to crunch numbers. They're going to give us the summary statistics. So the next thing we learned was what happens when we have two samples. In this case, a teacher wants to see if two different forms of an exam are equivalent or if one of the exams is more difficult than the other. Out of 120 students, she randomly sorts them into two groups of 60. And the group that takes exam A has a mean score of 78.1 and a standard deviation of 5.6. Now those percentages are there, but these are still mean scores. So even though they're in percentages out of 100, we're still going to treat those as quantitative data. An exam B average is 74.8 with a standard deviation of 8.7. So this is an example of sometimes you get percentages, but they're considered quantitative data because we can order those on a number line, we can average those. We want to know if these exam scores provide convincing statistical evidence that there's a difference in the difficulty of the two exams. Statistical evidence, or evidence in general, is always indicative of you need to write a hypothesis test. So the first thing we need to do is write our hypotheses, and we're going to hypothesize about two different groups of students who are taking two different tests. There's no indication that we should pair those up, that those students should one-to-one pair up, so we're going to consider these independent samples. So I'm going to let mu of, they've already given me A's and B's, so that's handy. Mu of A is the mean score of exam A, and mu of B is the mean, I can't spell, score for exam B. And this is for all takers. This is not for these particular 60 students and these particular 60 students. This is the mean of all people who take these exams. So the null hypothesis is that those two exams are equivalent. So the difference of the mean of A and the mean of B should be 0. And the alternative hypothesis, if I go back up here, I just want to know if they're equivalent or not. So they're equal or they're not equal. So this is a two-tailed test. So the mean of test A minus the mean of test B is not equal to 0 would be our alternative. We check the same conditions for a two sample t-test as we do for a one sample t-test, with the addition of saying that the two groups should have independent test scores. Okay, so do we have random samples? Yes, this is actually an experiment, not a sample. Exams were randomly assigned. I didn't really word that very well. I guess what I really should say was students were randomly assigned to exam groups. I did not do a very good job of wording that, but we're going to go with it anyway. We're going to assume that students taking exam A are independent of those with exam B. We're going to assume that 120 students is also less than 10% of all the students who take it, but technically this is an experiment. We probably could get by without this one, but yeah, we're going to do it anyway just to be sure. So 10%, my brain is not working this morning, y'all. Assume that these 120 students are less than 10% of all students who take the exams. That may or may not be true, but it's reasonable that if the teacher makes an exam, she might use it more than one time. And in the nearly normal condition, sample sizes of 60 are very much big enough. So sample sizes of 60 are large enough for central limit theorem to ensure a nearly normal sampling distribution. Picture of samples, sampling distribution. Okay, I feel fairly comfortable with those, so I'm going to say that we've met our conditions, and we will use a 2-sample t-test since we had independent samples. If we didn't have independent samples, we'd pair them up and do a paired t-test with just the differences and treat it just like a 1-sample. Okay, so mechanics. So we start with, if we want a picture, then we draw a picture. If not, we go straight to a t-score. Okay, the idea is if we took any and all possible groups of 120 students and broke them up into 2 groups and gave them the exams, their mean differences, or I guess their mean differences, y bar A minus y bar B, would be nearly normal with a mean of 0, which we hypothesize their difference to be 0, and we want to know where their actual means land. So we need a t-score with some funky number of degrees of freedom that we won't know till we run the test on the calculator. We have our summary statistics back in the paragraph, and it says that if we do group A minus group B, which is what I hypothesized, then we have a mean of 78.1 in group A minus a mean of 74.8 in group B, so that's the difference of our sample means minus the difference we expected, which was 0, over the standard error of our sample means, and that's that Pythagorean theorem looking formula. It is in your blue book on page 3. So the standard deviation of the first group was 5.6, so we do 5.6 squared over n, which is 60, plus standard deviation of group B, which is 8.7 squared over 60. And I do not have time to crunch all that out, so this is one that I would want to finish up on the calculator. So let's go to menu. There's definitely a glare on that. Statistics, stat tests, and this is number 4, the 2-sample t-test. I do not have data. I have statistics. And I'm going to have to give it all that information, so let me go this way. 78.1 for the first mean, 5.6 for the standard deviation, 60 for the sample size. Group 2, 74.8, 8.7, 60 for the sample size. Not equal to is our null. If we're asked to pull, we say no and enter. Scroll back up here a bit. Well, okay, so we have a t-score of about 2.47. So 2.47-ish, which is somewhat large. Degrees of freedom is 100.73-ish, so we'll just write that in as a subscript. We need to make sure we show that. And then the p-value is the probability of being at least that big, at least that high above the mean, so about 2.5 standard deviations above the mean or higher. And then this is a two-tailed test, so we want to see the mirror image down here. So 2.5 standard deviations or lower. Pretend it's beautiful and symmetric. So we need 2 times the probability of a t-score of 100.73 degrees of freedom, of 2.47 or bigger, and that is reported in our output here as 0.015-ish. So 0.015-ish, which is low, so we're going to reject. So with a p-value of 0.015, I will reject the null hypothesis at any reasonable, like 5% alpha level. There is evidence, always about the alternative, that the two tests are not equivalent forms. In other words, they don't have the same mean. They don't have the same average. Alright, once again, got a teeny bit of time left on this video. If you had to do a confidence interval, you would check conditions first. We've already done that. And then we would do the mechanics. So let's look up here to get our mechanics back. So we need the difference of the means, 78.1 minus 74.8, plus or minus T star with 100.73 degrees of freedom. Now that number's kind of, we are not expected to report what that actual t-score is. That's only true for that two sample t. Times the standard error, which is exactly the same formula that we used up here, 5.6 squared over 60 plus 8.7 squared over 60. And if we run that confidence interval in our calculator, and I don't have time, I don't think, to do that in the video, but you can do that on your own. You run the confidence interval and do a two sample t and input all of this just like we did for the test, and it's going to spit out for us somewhere in the neighborhood of 0.65 and 5.95. Because remember, this is a mean difference in scores, so we should be seeing some fairly small numbers. Okay. We are 95% confident that exam A has an average score between 0.65% and 5.95% higher than the average score on exam B. Alright, enough of that one. On to the next video. We'll take a little break here.